A black hole is a region of space where gravity is so intense that nothing, not even light, escapes. It emits no radiation of its own and reflects no light from its surface. For astronomers, this creates a logical dead end. If an object is truly, perfectly invisible, how do we manage to take a photograph of it? To find them, we have to stop looking for the void and start measuring the violent physical interactions it has with everything nearby. Because black holes are so massive, they dictate the behavior of the space around them, leaving behind structural signatures that we can map and measure. Most black holes are surrounded by an accretion disk. Gas and dust spiral inward, accelerating and heating to millions of degrees. This superheated material glows with intense radiation, creating a brilliantly luminous ring right before the point of no return. We are effectively looking at the glowing silhouette of the matter falling into the abyss. Einstein's theory of general relativity predicts that massive objects physically curve the fabric of spacetime. This curvature is so extreme near a black hole that passing light is forced to wrap around it, creating a bright ring of gravitational lensing. This influence extends to much larger objects too. At the center of our own galaxy, we've tracked a cluster of stars orbiting Sagittarius A star. Measuring these fast, tight orbital patterns allows scientists to calculate they are tethered to an invisible object millions of times more massive than our Sun. The black hole's mass is its own giveaway. It dictates the speed of stars and forces light itself to curve. While telescopes catch electromagnetic radiation like light and X-rays, scientists recently developed a way to sense the universe through a completely different messenger, gravitational waves. The LIGO facility acts as a cosmic ear. Its 4-kilometer-long vacuum tubes detect microscopic vibrations in the fabric of space-time itself. Cataclysmic events, like two black holes colliding, send out ripples that travel through the universe virtually unimpeded. Unlike light, these waves aren't absorbed or reflected by matter as they travel. By analyzing these specific vibrations, LIGO can determine the distance and mass of a collision without ever needing to see it. Gravitational waves provide all of this indirect evidence eventually led to the attempt to capture an actual photograph of the event horizon. Because black holes are so distant, resolving them requires a telescope the size of our entire planet. To achieve this, scientists synchronized radio telescopes across the globe to act as one giant Earth-sized array. In 2019, the Event Horizon Telescope released this image of the black hole in the galaxy M87. It was a historic moment, the first time we had ever seen the dark silhouette of the central void. That dark center is the black hole's shadow. It marks the boundary where the gravity is so strong that no light can reach our telescopes. The result was a direct visual match for the predictions of general relativity. It showed a dark central shadow surrounded by a ring of light, appearing exactly as the mathematics had suggested for over a century. However, the 2019 image was limited. Because the telescope array had large physical gaps between the stations, the resulting data was sparse, leaving the final image looking like a low-resolution blur. To fix this, scientists used a 2023 algorithm called PRIMO. It used machine learning to intelligently fill in the missing pieces of the dataset. The AI was trained on a library of 30,000 high-fidelity simulations. It learned the physical moles of how black holes behave, allowing it to predict what the image should look like in the areas where we lacked data. This reconstruction revealed that the bright ring of matter is actually 50% narrower than we first thought. This refinement significantly reduces the uncertainty in our calculations, allowing for a much more precise measurement of the black hole's mass. By combining the measurements of heat, light curvature, and space-time vibrations with advanced machine learning, we have moved from theoretical guesswork to high-fidelity observation. We are no longer just imagining the dark, we are measuring its dimensions.